All right, I'm going to give an update on computed phenotypes. I'm not sure if it was on the slides there because there's so much stuff in 1.8, but one of the things that was introduced was our digital twins and the computed phenotypes, along with the loyalty cohorts that were noted. Again, a lot of people contributed to the funding and development of this. So I've talked about this the last couple years, just going to give a quick reminder of it and then give some actual counts on sites that have been running this pipeline and generating phenotypes. So the challenge we have is that physicians must provide a diagnosis for patients even if they're just evaluating whether or not the patients have that condition. So across many different conditions, only about half of the patients who are coded with a disease actually have it. And a problem with this, of course, when you're running queries, doing this for a clinical trial, you get inaccurate feasibility estimates and fail to reach enrollment targets. So what can we do to address this problem? This isn't just one condition, it's across many different things. So this was a study 10 years ago at Vanderbilt, and they're showing that, for example, if a patient has a code for breast cancer in their chart, only 10% of those really have it. It's all screening tests. But if you look for 2 or more codes for that condition, then the positive predictive value of the code goes way up. But across many conditions, 1 code or even 2 codes is not sufficient to be able to accurately identify which patients have that disease. So we have the Venn diagram of the patients who are coded with the condition and the ones who really have it. The traditional way of building a phenotype is you get a group of clinical experts together and you create what's called a rule-based phenotype that says, I'm looking for patients who have this combination of conditions, laboratory tests, medications. You fine-tune this and validate it, and then after months and months of work and validation, you have your perfect phenotype for your institution. It may not translate well to other institutions. You have to retrain these, bring in the clinical experts again as data changes over time. So it's kind of the gold standard, but it's not very scalable. With new machine learning and AI methods, we can automatically generate phenotype models that calculate a probability or likelihood that patients have a medical condition. These are much more scalable and tunable to different institutions, and you can choose thresholds based on the types of errors that you're more willing to accept based on the research application. There's often a lot of confusion about what this computed phenotype pipeline means in I2B2. A lot of times people think that we are distributing I2B2 with a library of phenotypes. That's kind of often what that means. That's not what we're doing here. You're not downloading I2B2 and just getting out of the box a phenotype. This isn't also a group of experts that are going to help you manually put together your phenotype for your institution. Aaron over there gave me a great term called an automatic phenotype generator. I think that's really the ideal word for this. It's a software program that takes all the data that's inside of your electronic health record system and starts popping out different models. One regression equation for each disease that's represented in your patient population. So if you have enough data to train the models, this could be 1,000 or more different medical conditions. Each one of those have a phenotype that's been tuned specifically for your institution with no manual work needed. The work that clinicians do on a day-to-day basis to add ICD-9 code, 10 codes to patients' charts, that's the data that's feeding into it. You don't need any additional manual effort to be able to code or annotate and train these models. So as I'll show you the counts from different institutions, this is really scalable in a way that's very different than how people think about phenotype creation. So there's a couple algorithms that go into this pipeline. The first is Kessler. This is using something called embedding regression to take all the co-occurrences of codes in your system and figure out what concepts or clinical features are most relevant to a disease. So we'll see that type 2 diabetes has co-occurrences with things like insulin and hypertension. retinopathy, obesity, and it'll identify those as related to your condition. But that alone is not a model. The second step is called COMAP. That then uses aggression to assign weights to those different features. And that's where now you have a machine learning model. So when I have a new patient, I can take the codes that are in their chart inside of I2B2 or OMOP. I can run them through these weights, and out will come a score that says the likelihood of that patient having that condition. There's a default threshold, and the patients above those thresholds get a code inside of I2B2 saying that they likely actually have that condition versus the raw code that the clinicians entered. I'll mention that the science behind this was developed by Tianxi Kai and her colleagues, and she's been here in past symposia to talk into those details. I have worked with the I2B2 teams to help implement that, those algorithms inside of the I2B2 software. So one of the questions that comes up when we're talking about these models is, why don't we just use large language models to ask, does this patient have the condition? And you can do that, but there's a high cost to computation. And large language models work great when you're working with nodes for maybe a few thousand patients. But when we're looking at 1,000 different medical conditions across millions and millions of patients, it becomes really slow compared to the computed phenotypes. We can generate 1,000 phenotypes within a few days of compute and assign those to millions of patients. So it may not be perfect, the methods that we're using, but it's very, very scalable, and it gives you a first pass that's better than the raw codes in the EHR. Certain phenotypes may require complex multi-processing steps, which are harder to do with a single LLM prompt. There's uncertain performance on low prevalence diseases and rare conditions. And there's general LLM concerns such as hallucinations and ethical issues. So what we see is maybe an ideal combination of using both more traditional AI methods and LLMs is that you can first use these computed phenotypes to create cohorts enriched with patients with a condition. It doesn't cost a lot. You can search through millions of patients and find the patients that are very likely to have diabetes, for example. And then you send those patients to an LLM, and then it can pull up the nodes and refine that list to optimize the cohorts. So you'll hear from AI with Care that's been doing some of that exact same thing a little bit later today. About how, what we're doing here is really the raw codes to the first step of cleaning that up, and then you can build manual rule-based phenotypes or large language model used to get to the final steps. So these are some of the site counts, at least that we know about so far. Mayo Clinic has developed phenotype models for over 1,600 medical conditions, 1,400 at MGB, 1,100 at University of Florida. At Beth Israel, we have a smaller population. You need a minimum number of patients for these models to converge. Since we have a smaller group, it's about 983 models. And then Pittsburgh and Houston have run sort of we have a smaller subset of phenotypes that have been validated at multiple institutions, which you can use as a first pass just to make sure your pipeline is working at your institution before turning on the full pipeline of it. So as you can see on the third column, individual patients may have multiple medical conditions that is fine, so you end up with tens of millions of phenotype patient pairs out of this system. And it's not just a phenotype for a disease. Because of the scalability of this, you're finding not only the patients with diabetes, but now you have an accurate representation of all their comorbidities. When you're looking at rule-based phenotypes that find just the patients who have diabetes, if you don't have all those other phenotypes, you're still using the raw codes to figure out whatever else they have. So we're both finding patients and getting a better picture of their health using these very scalable phenotype models. When we do manual chart review, we're not using it to build the models, but to validate and check what their accuracy is. These are, as I said, you don't need any manual effort to train them, but it's helpful to check them afterwards. When we look at different medical conditions, some of them, the diagnosis codes work really well, and you don't really need machine learning to improve on them, but those are pretty rare. The most conditions, the computed phenotypes greatly increase the positive predictive value. They have pretty good recall, and they're much better than the raw diagnosis codes. Most other phenotype models, they'll perform at least as good in terms of positive predictive value as the raw diagnosis codes, usually a bit better, but sometimes they suffer from lower recall unless you do some manual tuning and improvements of that. As we begin deploying these computed phenotype models at multiple institutions, you can use federated learning to improve the robustness of the models. We talked about this a little bit earlier, and that in model trained only at one site can have a risk of overfitting, but if you're pulling together the co-occurrences from multiple institutions, you get a much more sort of stable picture of what features are associated with conditions and building your models off of those. So as people start using these, we're looking for volunteers to come together to start working on some of these federated learning-based computed phenotypes. And I'll stop there and see if there are questions.
So, Griffin, one of the things that confounds my research is patients who get a diagnosis and then it ends up being a misdiagnosis. Do you have a way of identifying misdiagnoses?
Well, misdiagnosis is similar to diagnosis codes that are put in for billing purposes where they don't really have it. So the patients who truly have the condition will be coming back over and over again for that. So the way the algorithms work is they look at frequency or multiple occurrences of a condition relative to healthcare utilization. So if a patient has been to your hospital 3 times and all 3 times for diabetes, they probably have diabetes or seeking care for it there. If they have 100 visits at your hospital, only 3 of them mention diabetes, it may have been they were being evaluated for it or it was an incorrect diagnosis until it got fixed into the chart. So you look at both of those things plus the other features in there to figure out what conditions the patients have. But these wrong diagnoses could be because of billing, because of misdiagnoses, typos. You see certain pairs like type 1 and type 2 diabetes or ulcerative colitis and Crohn's disease, where the physicians kind of flip back and forth on the conditions until it's sort of stabilized until what the patient actually has.
Hey, Griffin.
Yes.
I just listening to you and Jeff, I'm very happy. Do we have explicit control of namespace such that, let's say, IMO, ICD, OMA, ICD-11, so could we have that out as like differential feature fee codes? Where are you on, thinking on like the fee codes? And so, I'd love the differential comorbidity patterning, but in what namespace are you going to do that?
So the computed phenotype pipeline starts with a set of features, and you define what you mean by a feature. So by default, it's using fee codes, not the actual ICD-10 or ICD-9. So it's first mapping your local diagnosis codes to fee codes, and then using those as the inputs.
Really fine, but how do we estimate the amount of precision that has per patient, and then what's the gap between a fee code and like a SNOMED representation of a name?
Right, so that's where you're going to introduce some error. And then the code comes up, can we create a computed condition for a disease that doesn't have a code for it? So that's where you do need a gold standard or silver standard data set to label patients that you think have that condition rather than an ICD or fee code. And then that can feed into the same model and you're building something off of that. But that's an important step. That mapping and what you define as a feature is important for the downstream analysis.
Where you can get a domain expert to really put their kidneys into that.
Yeah, I mean, for long COVID, that's where a lot of work is done. Mm-hmm.
I was wondering what input variables are given to the regression models, and if there's like any differences in how each institution codes for these, if that would lead to maybe making it more difficult to do that federated learning across multiple institutions coming together.
Right, so the Kessler algorithm is the part that figures out what those features are. So it looks at co-occurrences across many different domains, diagnoses, laboratory tests, procedures, demographics, and it finds which features seem to co-occur more often than expected with your disease. And it's usually about 200 or so features out of the million that are in the ontology. Then those 200 feed into the COMAP algorithm, which assigns the weights. When you're training these within an individual institution, you'll get different features. There'll be some standardized things. So you're always going to see like insulin with diabetes, but then at the tail end, there'll be different things from each institution. That's where the federated learning comes in, so that you're not pulling in something that's overfitting, but something that's more generalizable across different sites.
Thank you. That's a lot more clear. And one more question. Have you considered using other models? Maybe you are, like other than just a simple regression, like a neural network.
Yeah, so I'm picking the simplest version of this algorithm that my colleague Tangxi has developed, but I mean, they've done much more sophisticated parts on this. What's nice about this is the scalability. It's simple, but I can run this within a couple days at most institutions across 1,000 different conditions. It's easy to understand and look at it and kind of double check it. So again, this is, I'm trading off sort of accuracy for the scalability and simplicity of it. And then you take the output of this and can feed it into more complex models that will refine your cohorts.
Thank you.
All right, thank you.